Morning, everyone. I'm so excited to see all of you in person today. Welcome to our KISS workshop, where we will be looking at how we target microhabitats in icy environments so that we can further ocean world's exploration, hopefully in the next decade, but we'll see how it goes. I'm sure there'll be questions throughout the day and we'll answer them as they come up, but for now, I'd really love to introduce my personal friend and the first of our speakers, Michael Malaska. Mike got his bachelor's in chemistry from MIT and a PhD in chemistry from UC Berkeley. He actually worked in pharma for a while and then got super excited about the Cassini mission and decided to move to planetary. And we are all so lucky to have him with us. So Mike, take it away.
Thank you, Charity. All right, would like to welcome all of you, as Charity said, to this conference. I'll be the first of 4 presentations that will be kind of trying to get us all on the same page with respect to microenvironments and why we're all here for the next week. So I want to show you this slide, which is the title slide, which is showing you our customer. When we go out looking for life on the ocean worlds, this is going to be the example of something that will light us up and get everybody excited. This is a picture of a diatom. It is embedded in kind of like a slightly rocky matrix, but this was actually extracted out of a Greenland ice core. And if you look at the size, that's only 5 microns across. It's tiny. And it's going to be a repeating theme of what we're going to be focusing on here today, is how do we focus on super, super tiny places where super tiny organisms can live. So the general big theme that we're going to be exploring is life pretty much in ice, maybe permafrost, and also in small environments and niches in the rocks, but focusing on predominantly icy worlds because there's a lot of ice and a lot of liquid water environments in the solar system. And each of these worlds is potentially a very high astrobiology target. From left to right, we have Europa, Ganymede, Callisto. We can debate on Callisto, but I think it's interesting astrobiologically as maybe a null case. Tiny, but very important Enceladus, big, huge ocean world Titan, and then even further out we have Triton, and there's a chance that there's other worlds like Pluto and Ceres and other things that are of interest as well. There's a huge amount of real estate and a huge volume of ice to explore. So when we're thinking about ice on other planets, the Earth and Mars both have what I call depositional ice. At the very tippy top, you have snowfall, maybe you have frost deposition, and it kind of is only at the top little few kilometers of the surface of those worlds, and only in a couple places. When you move to Enceladus, or the ocean worlds, you have this very thick shell of ice, and then deep underneath that you have an ocean, and then way down below that you have sediment. These graphs are kind of shown at log scale. So, 1 kilometer, 10 kilometer, 100 kilometer, then all the way down to the core. When you get to things like Europa, larger ocean worlds, there you have a stagnant lid of ice, which is stable and it doesn't move. And then underneath that, you have these huge convection belts of ice that are moving around, the ductile layer. And there it goes down to the ocean, comes up to the top and cycles down. And you have tiny little areas of frozen ocean water that's migrating all the way up and then descending all the way down over 100,000 million year timescales. As you get to larger places like Titan, it's actually so big that underneath the ice and underneath the ocean, you actually have a higher pressure ice that's actually more dense than water because of the intense pressure. And it turns out that those too can convect. So there might actually be other microenvironments in that super deep ice layer under the large ocean worlds like Titan, Ganymede, and I think maybe Callisto can do this as well. But this is the really key slide that I want to show off. This is some work done by Karen Young et al. And what's really cool is this is an image of ice that was taken from the Chugach Sea. So it's frozen sea ice. And you see this place where there's 3 ice grains coming together and they make a triple junction. And right at that triple junction, there's a zoom of it up in the upper right, 10 micron little tiny pocket where these 3 little cracks between the grains come together. And in that little spot, if you light it up with epifluorescence, you see 2 little bacteria. So it's a tiny little room in this big vast amount of ice, but there's 2 bacteria that are living in there. That is a great example of a microenvironment. It's not very big, but as anybody who's ever rented an apartment in New York, you don't need very much to be able to live in, right? So it's a tiny little spot, but they're totally happy. And that is one of our targets. When we think about ice going down deep, like deep down into the ocean worlds, is pressure a problem? And it turns out no. You can isolate living bacteria from about 3 kilometers down underneath the Greenland ice sheet. This is part of the GISP-2 ice coring project. They extracted these bugs up. And a couple numbers that I want you all to kind of remember is 264 Kelvin, I think in Kelvin, sorry, but it's maybe, was that like minus 10 degrees Celsius, and 30 megapascal. So it's under quite a bit of pressure down at the base of the Greenland ice sheet, but they're able to isolate microbes in there. When we're thinking about other ocean worlds where the gravity is less, that 30 megapascal is right about the transition zone where you have that convective ice and the brittle ice. So there are places in our solar system that have those very same pressure and temperature conditions in an icy environment. So you can have the natural logic, if bugs can live on Earth at those conditions, they should be able to live in those other places in ocean worlds on the solar system. So that means that when we're looking at a lot of those worlds, it's all habitable, pretty much. So the big lesson is that the deep ice environment is going to be the first habitable environment that we're going to hit on our way drilling through the crust going to the ocean. So there's a huge push right now to figure out eventually how can we drill down into the ocean. And what I want to be able to state and what kind of our purpose here is to figure out how do we look for microbes that are in those little tiny pockets in the deep ice. That's the first thing we hit when we're going down through the ocean ice crust. Okay, so focusing back on the exact conditions. Here's a slide which talks about the potential for habitability, and I'm going to state that, yeah, it's habitable. The pressure and temperature conditions are just fine for microbes. I've drawn a picture of the Europa temperature profile, the Europa pressure profile at depth, and you can see these little squares, and those squares correspond to environments where these 2 microbes can exist, perfectly happy. I am not a microbiologist, and I know in this room we have some serious microbiology expertise, so you guys probably have stuff in your freezer or that you've explored and studied that would be replacements for these. So we have microbes that you could put down there and they would survive just fine. So that cracks the definition of habitability. My own personal journey into understanding about microhabitats started on the Greenland ice sheet, where we were taking an instrument and then drilling down to about 100 meters to look inside the ice, to look at the spatial distribution of organics. Here is a picture of that. Oh my gosh, this is actually the video works. Okay, cool. So there's the video. This is us raising our instrument out of the deep ice. We had a deep UV fluorescence instrument that was scanning inside the ice at about 100-meter depth, looking out and recording any types of organic signals that were fluorescent and basically seeing what's down there. And what we expected was to see a bunch of layers. Here's an image of the GISP-2 ice core, which is taken, maybe a few kilometers away. This is at a particular, much higher depth, but same sort of deal. You'd expect glacial layers and stuff like that, deposition. When we lit it up with fluorescence, over on the right, we saw something very, very different. We did not see layers, we saw spots. And we saw these little fluorescent spots. And even more important, we saw little small spots, and they were separated from each other, and they were different from each other too. And if we look at another image, you can see the different colors correspond to the different lambda maxes, which is effectively different light wavelengths that are being emitted. These are different chemical environments. So just looking at this, you see 5 different colors. And that corresponds to different, well, actually 4 different environments. So you see the yellow stuff, you see the red stuff, you see the blue stuff, and you see that really, really intense purple stuff, which is so bright that it's actually saturating out the detector. So there are, oh yes, sorry.
So this is a pseudo-color, right, that it is actually corresponding to these wavelengths that are basically violet and UV, is that correct?
Yes, yeah, sorry, let me, so there's a question is like, what exactly are we looking at here? And what we're looking at is, I've taken the different wavelengths that are all in ultraviolet or fairly short wavelengths, and I've transferred them to different colors. So red is going to be a longer color, and blue is going to be a shorter color. Blue in this case is right around 310 nanometers, and red in this case is about 415, say, nanometers. So we see the different colors, and that's telling us that there's different chemical environments. The other thing it tells us is that the spots don't seem to have much of a relationship between each other, right? They could be just random. And there's uniform across the spot as well. So while they're very different from each other, they're also uniform inside the spot. So it's almost like a pure, tiny little microenvironment that we're seeing, at least with respect to fluorescence. We looked in the literature, and it turned out that this is sort of like a recurring theme. So here are some other images from using other different techniques. One of the ones that repeats often is using deep UV fluorescence. It works really good at this sensitivity and scale. But there's other techniques as well, such as using nanosims with a silver plate pushed up against to look at sulfur isotopes, using mass spectral imaging of some deep sediments, and again, laser-induced fluorescence with a different wavelength. And you see this repeating theme of spots. We dug in the literature some more, and here is sort of like a cartoon that shows the different type of ocean world environments that we would expect to see when we explore the ocean worlds. You have the upper crust, you have the deep ductile ice, you have maybe sort of like a re-melted lens that maybe they're proposing for, say, Europa or maybe even Titan. You have this convective deep ice, sea ice, which would be in contact with the sea. Maybe going down even deeper, you have microbial mats, you have bottom sediments. And so we were able to pull all these like little analog environments out, and sure enough, it looks like you're seeing spots, and the spacing is right about the same. So we were able to keep kind of like a database, a collection of all the stuff that people have seen to help us figure out what are the characteristics, common characteristics of microenvironments that would see maybe on an ocean world. And just sort of like a quick summary of what we saw is that things like to clump. And it's somewhere between 100 microns to a millimeter across of spots. Individual spots are uniform. They can be diverse from each other, and we see them throughout these different Earth environments that are analogs to the ocean worlds. So let me present kind of like how we think these might actually be forming, some of the physics of the ice that helps form these spots. As water freezes out, ocean water, rainwater, whatever, the first thing that happens is you start getting little nucleation of the ice crystals, and as they grow, the pure water molecules are finding their happy space in the crystal, and they're pushing everything out that doesn't really fit in the crystal. So all the impurities don't make it into the ice crystal. You're crystallizing out the pure water, and so everything else goes into the gaps between these growing grains. As the grains get larger and larger, they start to concentrate the remnant stuff in these tiny little spots around and between the different grains. And so what eventually happens is you end up getting, as long as you don't totally freeze it out, you end up having a liquid environment because you've increased the salt concentration, so you lower the effective freezing point inside that tiny little pocket. And here's a table that shows maybe a zoom in of a section of the GISP2 ice core, which was deposited from snowfall, compressed down. You have these big, huge grains, and they used a Raman microscope to be able to interrogate the different veins and see what the chemical composition is compared to the original ice grain. And you're getting these incredible concentration factors. 200,000, 400,000 for these different salts. If you're a microbe and you like to eat sulfate, this is basically giving you your concentrated food for free. So this is making those little microenvironments a super great place to live because you've concentrated all of your nutrients into that little zone. There is a trick. And the trick is that if you are a little microbe and you want to stay in that little vein and not get stuck in the ice, you got to be a certain size. These authors did a really cool amount of research where they used little tiny fluorescent beads to see which bead sizes get incorporated in the ice and which can get squeezed out and migrate with the grain. And what they found is that the magic number is about 5 microns. So if you're bigger than 5 microns, you're going to get stuck and embedded in the ice and you're going to be frozen and not having any food. If you're smaller than that, you will effectively surf the freezing front and end up in the liquid zone and be totally happy. So that gives us our big clue, and a constraint that we have to worry about is that in order to be inside that liquid pocket, you have to be really small. Here's a quick picture showing some comparison of some cell sizes. Red blood cell, 8 microns across. E. coli, Staph A, Mgen is all fairly small, maybe about 0.5 microns at the smallest. When they looked at microbes in these deep ice cores, they found that they were super tiny. They're about 0.2 microns across. This is getting to the size of really big viruses. So it's between really super tiny bacteria or really big viruses. And most filters are usually about 0.2 micron filter holes. So here's a picture up here showing 2 microbes that were basically happily cuddling together, so they didn't fit down that hole in a filter. If they were single, they would have probably shot right through. So when we're starting to think about looking for microbes and we want to use any type of filtration, we need to have these ideas in mind so that we don't lose the microbes through the net, as it were. It also means that our targets are very tiny. And this is a rogues gallery of a whole bunch of different bacteria with these different scale bars. These are all things that have been isolated in 3 kilometers deep in the Greenland ice sheet. Again, conditions that would be equivalent to an ice shell on other worlds. So it's very likely that the physical processes that constrain size here on Earth are going to adapt or apply as well to other ocean worlds, so they're going to be fairly, very small. Right, so what that means is that you have these tiny little microhabitats in the ice. So we did the math of looking at how many of these microhabitats could exist. And when we realized, they're like a micron or, a millimeter across, we see how many that there are in our images, we figured out that there's more microhabitats in the Greenland ice sheet than there are stars in the Milky Way. And that when we think about this in terms of how many environments of this size could exist in the ice shell of Titan, we come up with a really high number that's like bigger than the number of stars in the entire universe. So these are really huge numbers because they are so absolutely tiny. So it's a great diverse set to be exploring for as we plunge our way through the ocean worlds. So how would we do this? I've kind of come up with sort of a rough flow chart that will be kind of the themes that we will be exploring in this workshop, where you're going to have some type of a detector that sees these microhabitats. You figure that something is maybe important, you go after it, you figure out exactly how to precision target these your physical acquisition system. You're going to punch in and grab that from wherever material you're exploring, bring it on board your spacecraft or testing system, move it around through piping, go to some type of instrumentation that can tell you whether it's living or dead or what, and then you're going to relay that data back. And this is sort of like the basic idea that you would do in planetary exploration, and you may need to do it as well for terrestrial exploration as well. Thinking about this, your first step of microhabitat detection, from our work looking at the literature and also our own work, it turned out that deep UV fluorescence is probably one of the best ways to do it, because it's very good to get you the scale that you need to be able to see, as well as the sensitivity. There's very small trace amounts of this material in ice, and this is a really great technique, and it's almost flight ready. Other techniques are possible as well, nanosims, epifluorescence, but those may not be easily adaptable to flight conditions, and there's probably other potential instrumentation techniques for detection, and those are the things that we'll be talking about in the next few days, or next day, of our workshop. When we looked at this, one of the things that we discovered is that there seems to be different sizes that kind of cluster up. So there's the level of the individual microbial cell, so that's super tiny. There's the house of the microhabitats, the micropocket, 10 to 300 microns about. And then there seems to be this super organization of larger things at about 1 millimeter or 1,000 microns. Here's sort of a picture which shows the different data sets that we've looked at in the literature. And this kind of shows the numbers of ranges of the sizes and kind of the natural clustering and the types of environments where we've seen them. And this is kind of like how we've sort of tried to rationalize how these fit together. At the individual cell, you have super tiny. They can live maybe inside a house, and that's the equivalent of a microhabitat or micropocket with a few cells. And then it seems like there's this larger organization that we call the ROI, or region of interest, and that's what we detected with our fluorescence measurements. And that seems to be maybe several different micropockets that are all kind of the same. So they seem to have a sort of a uniform composition, but they're much larger than the individual micropocket cells. Maybe there's some type of communication between them. I don't know. That's stuff to figure out. But it's those villages. And then when we're looking at those huge scenes, we're seeing these different villages kind of scattered around in the landscape. Thinking about how we actually acquire these things, you have questions as to how do you actually drill out a sample? Some of these are going to be weird, goofy shapes. So you have to figure out what's going to be my target diameter. If I want to get the maximal purity of something, no extra matrix, I may need to have a very small target. If I want to get everything, all the maximum amount of material, I have to have a very large target acquisition area, but then I might end up getting some of the surrounding matrix, or I might get some of a surrounding spot too if it's really close. So these are all kind of the things that we have to worry about as part of this workshop. Here's another slide which shows the different scales that we can think about, images and acquisition diameters. And the key is that targeting these is going to be a real hard challenge. And I'll show you an example map from what we saw in Greenland. Here is one of our maps that we published, and I've overlain some little tiny excision circles around it. And you can see in a couple cases we have a little bit of overlap. That's going to be a problem. We have to figure out how we're going to deal with that. But in one case, we have two clean acquisitions of two totally different types of spots. So if we were exploring on another world, this might be a really good thing to do. We see two different things. We acquire both of them in the same scene. We figure out that they are or are not of interest, and then we can move on to the next sets of spots. Next question is, when you do acquire these things, well, how do you do it? And then how deep do you go? So if you go right at the very surface, you may need to only go a certain size of that diameter. If you go deeper, you might get more of that. And then the other question is, do you want to be really, really sure and go in and core to set depth? And the thing that really helps out is trying to figure out how much materials you actually have. I realize I'm showing tables, but these are going to be in our common drive so we can see these numbers. So that'll help us figure out moving forward how much volume we're actually dealing with when we're talking about acquiring stuff and moving it around. So what's interesting is that when we do typical bulk concentration, you're melting everything down to get to the good stuff. In this case, we're only getting the good stuff. So the amount, the quantity is the same, but the concentration can be up to 100 times more because we're only getting the stuff we want and none of the surrounding water or liquid, ice that will be diluted out. So that can allow us to go above the limits of detection of instrumentation, where before our dilution may have put it below the detection limit. Here's a plot that was put together by Aaron Noel that talks about the different types of instruments and where we are in terms of targeting microenvironments, and showing that there is a technology gap, that we need to figure out how to do single microliter to even nanoliter manipulation to be able to move these small, tiny quantities and volumes around. Here's the last slide, and this is again an eye chart, but it is something that we can use for our work, and it basically provides the background of, well, when we looked at this, here's the optical size that we would need to acquire, here's about the resolution that we would need, here are the techniques that have been used in the past to be able to get to this. And then when we're talking about acquisition, what's the diameter range we need to worry about, and cell concentration. And then the big one is that what's the actual volume in microliters or nanoliters that we have to deal with, and then how many cells could we expect to see in these microhabitats. And I'm going to summarize it all up now by saying that one of the things that we found is that life likes to clump. So there are these tiny little microhabitats. The spatial distribution of these, we have 3 sets. We have the ROIs, we have the micropockets, we have all the way down to the cells. There could be even higher orders of organization that we don't know about. There is a significant advantage to targeting these things, primarily in terms of seeing the actual diversity that's there, getting the spatial context. But the big challenge for us and this workshop is how do we adapt the new techniques and instrumentation and technologies down to a small scale to actually be able to target these. And this is what we're going to be trying to work out over the next few days with some of the experts in all these different fields that have been pulled together at this workshop. And so with that, I'd like to thank you all, and I'm open to any questions.